He's the ACM-ICPC World finalist. He's also a longtime teacher in Accent. Okay, thank you, Yibo, for coming. Turn the stage to you.
All right, great. Yeah, so let's go over the goal problems here. Oh wait, okay. Yeah, so for our three goal problems, we had cow dependence, interstellar intervals, and job completion. So the knowledge required for the first problem is like square root decomp, binary search, and/or ad hoc. For our second problem, we have a relatively standard dynamic programming problem with some optimizations needed. And for the third problem, we had a greedy. Now, the XCAM courses that covered all this knowledge are going to be 400, 401, 602P, and 602. Okay, let's go over the actual problems themselves. And I'll go over them in order of like easiest to hardest, in my opinion. So I think the easiest problem of this contest was probably the third problem, job completion. For this problem, we're given a bunch of jobs, and for each one, we choose to complete it or not. And if we choose to complete it, we have to start it at or before some time s of I, and it takes t of I time to complete. So this problem, if you try to just solve it in this format, is actually kind of tricky. Let me give an example. So suppose you have one job that you can start at time 1, but takes 10 units of time to finish. And you have a second job that you can start at time 3 and takes 1 unit time to finish. One idea might be, well, maybe you can sort them all by start time, but it turns out this actually doesn't work that well. Because what you would have is if you start this, if you schedule this first task to be started at time 0, for example, then you can't schedule the second one. But there's actually a way to fit both if you were to schedule the second one within your first time slot, and then schedule your next one in the next 10 units of time. And so this is a case where it can be very, very tricky to do, even if you do like some sort of sort by start time and then some DP on if you should take it or not, it doesn't quite work, right? Okay, and then similar problems happen if you try to like go backwards in time. So the big observation for this problem is that we actually don't want to deal with the start times. We want to deal with them in terms of deadlines. So let's just briefly convert this problem statement a little bit. So if we're given the deadlines of every project and the time it takes to complete them, then we would have this first project's deadline is at time 11, and the second one is at time 4, right? So this is the exact same problem. All we've done is we've added the time it takes to the start times of each project to get the deadlines of each project. And now we can sort by the deadline time, and now it makes sense, for example, to use like a DP solution to figure out for each of our projects, should we take it or not? Okay, so this would be an idea you can use to get the first or like inputs 3 and 4. So you can do some sort of DP on the index and how much time has already passed. Okay, and I think you can do something very similar for the n is up to 2000 case, where basically you can still DP on time and index, but the time dimension, you probably need to like corner compress or something to make it work. All right, so let's go over how we actually solve this whole problem, which is once we've sorted them by deadline, we notice that like in general, since all the tasks are weight 1, as in you only get 1 point for completing any task, in general, we want to do this like fastest jobs first, right? So one idea could be you can now sort them based on their timeline. or like their time to complete and go through them in order of like smallest time to largest time and try to add each one. But it turns out it's still a little bit tricky to figure out how to schedule them to make that work. So instead, we'll do this another way where we sort by their deadline. And essentially the idea is for every single task, we're just going to try to take it whenever possible. And whenever it's not possible to take a task, we can kick out an existing task that we've taken previously, as long as that task that we kick out takes more time. So let's go through our example here. Let's just add maybe, let's add, okay, let's add some. So let's say we have 4, 1, 11, 10, and then we also have like 12, 4, 13, 7. Okay, something like this. So first of all, our optimal solution should be to take this task, and this task. But that being said, the optimal solution, if you only have the first 2 tasks, would be to take the first 2. So yeah, we need our algorithm to work regardless of if it's like just this prefix of the array in our input or the whole entire array, right? So let's essentially try to compute the optimal solution at every single step. So the first thing we see is this task of time that's due at time 4 and takes 1 unit of time to do. So let's just go ahead and do it. Okay, then we get to our next task and we see, okay, we can actually do this task because now our total time needed is 11 and this is due at time 11. So we can just take both. Great. Now for our next task, we see that we can't schedule all 3 of these because this takes a total of 15 units of time, but this task is due at time 12. So what we're going to do is we're going to kick out the task that took the longest to do so far. And now we can add in the new task, right? And now we still have 2 tasks, which is the best we can get among the first 3 elements. But our total time taken is now only 5 as opposed to 11. So it is like the most optimal solution up to this point. And then finally, for our last task, we can just go ahead and add it in, because this now takes a total of 12 units of time, and we have 13, right? So we can output 3 for this example. Okay. So quick note about like some implementation details. So first of all, the data structure we need to figure out what's the so first of all, yeah, so we're going to keep like a priority queue to track all the tasks that we've taken so far, and they'll be sorted based on how long it takes to complete them. And then whenever we try to add in a new task, what you can do is you can just always add the new task into the priority queue and also increment the total amount of time that it takes. And then if the amount of time it takes total is going to exceed the amount of time so far, then you can just take out the biggest element out of this priority queue and decrement your time by that amount, right? So let's just run through this really quick one last time with our example here. So here's our priority queue. We loop through the first element, and then our total is currently 0. So we loop to the first element, we add it into the priority queue, update our total, and we see we don't need to kick anything out. Go to the second element, we add in a 10, and now our total is 11, and we still don't need to kick anything out. Now for our third element, we just go ahead and add 4 into our priority queue, and now our total is 15, which exceeds this 12. So we have to take out the biggest element. Let's go ahead and remove the 10 from our priority queue and also decrement our total by 10. And then finally, we get this element. So we just add in a 7 and our total is now 12. So we don't need to kick anything out. And then at the end, our answer is just whatever the size of our priority queue is. Okay, yeah, so that was problem 3. I think probably the easiest problem of this goal contest, assuming you've seen some sort of similar greedy problem before. If not, if this is like the first time you're seeing this priority queue greedy technique, it can be very tricky to figure it out.